Hello, my name is Habibullah and I'm here to represent my topic Heads-up display technology projection for pilots. First of all, what is a heads-up display? A heads-up display is also known as HUD is a transparent display that presents critical data on a screen or glass surface in front of the users so they can keep their heads up and stay focused. The main purpose was to avoid pilots losing situational awareness because they had to look down at cockpit instruments during high speed, high stress operations. Nowadays, heads up display is not only limited to airplanes but also cars, helmets, and other consumer techs as well. The history and evolution of heads up display technology started in the early 1940s. Heads-up display evolved from the reflector sight, a pre-World War II free optical sight technology for military fighter aircrafts. The gyro gunship added a rectile that moved based on the speed and turn rate to help in hitting a target while maneuvering. The telecommunication establishment in charge of UK radar development found that Royal Air Force fighters were having a hard time reacting to the verbal instruction of the radar operator as they approached their targets. Pilots needed a way to aim weapons without looking down at gauges. They experimented with the addition of a second radar display for the pilots but found they had trouble looking up from the little screen into the sky in order to find the target. In October 1942, they had successfully combined the image from the radar tube with a projection from their standard GGSMK. A simple illuminated rectangle was projected onto a glass plate, allowing pilots to aim while keeping their eyes forward. This was the foundation of the modern heads up display. British Royal Air Force played a major role in developing early heads up display systems for jet aircraft. After the war, engineers began experimenting with displaying flight data on reflectors. Heads up display technology research was uplifted by the Royal Navy in the Buccaneer, the prototype of which first flew on 30th April 1958. The aircraft was designed to fly at a very low altitude at very high speed and drop bombs in engagement lasting seconds. As such, there was no time for the pilots to look up from the instrument to a bomb site. This led to the concept of a strike site that would combine altitude, airspeed, and the bomb site into a single gun sight like display. There was competition between supporters of the new heads up display design and old electromechanical gun sight. Initial production units were built by Rang Sintel and the system was first integrated in 1958. The Sintel heads-up display business was taken over by Elliott Flight Automation and the Buccaneer heads-up display was manufactured and further developed, continuing up to a Mark III version with a total of 375 systems made. It was given a fit and forget title by the Royal Navy, and it was still in service nearly 25 years later. BAE Systems thus has a claim to the world's first heads-up display in operational service. A similar version that replaced the bombing mode with missile attack mode was part of the Air Pass heads-up display fitted to the English Electric Lightning from 1959. In the United Kingdom, it was soon noted that pilots flying with the new gun sight were becoming better at piloting their aircraft. At this point, the heads-up display expanded its purpose beyond weapon aiming to general piloting. In the 1960s, French tested pilot Gilbert Klopfenstein created the first modern heads-up display and a standardized system of heads-up display system so that pilot would only have to learn one system and could more easily transition between aircraft. A heads-up display works by projecting critical information directly into the glass in front of the pilot, allowing them to see data without looking away from the outside environment. The system first collects real time information from instruments, sensor, and navigation systems, which is processed by the heads up display computer into visual symbols such as speed, altitude, flight path, or warnings. This information is sent to a bright projector, which generates the image and passes it through a series of optical lenses and mirrors called collimating optics. These optics make the image appear at optical infinity, allowing the eyes to focus on both the heads up display and the outside world simultaneously without strain. Finally, the image is reflected off a semi transparent combiner glass placed in front of the pilot, creating a stable floating overlay of digital information on top of the real world view, enhancing situational awareness, reaction time, and safety. Heads-up displays simplify complicated data into a clean, easy to read visual layers. Let's break it down into simple steps. First, the heads-up display systems receive data from the aircraft sensors, and then a computer converts this data into symbols and graphics. These symbols are then sent to a display projector. Inside the heads-up display is a projection unit that uses a CRT, LCD, or LED display. This projection creates a bright image of the symbology and is also a light source. Then, a combiner glass is used. The projection image is directed onto a special transparent glass called the combiner. This combiner reflects the heads up display information back to the pilot, transmits the outside world view through the small glass. This creates the illusion that the information is floating in front of the aircraft nose, usually about 2 to 4 meters ahead. After that, heads-up display ensure the image is collimated and meaning the image appears at an infinite distance. Because of the collimation, pilot does not need to refocus between outside world and heads-up display symbology. This is the key reason that the heads-up display improves situational awareness. After that, as the captain look through the combiner, they see the real world and plus the overlaid symbology. The symbols move in real time according to the aircraft motions, which make the reading of the symbols and heads-up display more easy. And in the end, the heads-up display receives the information from air data computers, internal sensors, GPS, radar navigation, and etc. And all data is integrated and updated many times per second. With the pilot experience, when looking through a heads-up display, the pilot sees a floating display aligned with the outside world. Data that moves naturally with aircraft orientation, no need to look down, change your focus, and search for instruments. This reduces workload and helps maintain constant situational awareness for the pilot. Now let's come to the design factors of the heads-up display. There are several factors that interplay in the design of the heads-up display, like field of view. Also, FOV indicates the angles vertically as well as horizontally. A narrow field of view means that the view through the combiner might include little additional information beyond the parameters of the runway environment, whereas a wide field of view would allow a broader view. For aviation application, the major benefit of a wide field of view is that an aircraft approaching the runway in a crosswind might still have the runway in a view through the combiner, even though the aircraft is pointed well away from the runway threshold, whereas with a narrow field of view, the runway would be off the edge of the combiner, out of the heads-up display view. Because human eyes are separated, each eye receives a different image. The heads-up display image is viewable by one or both eyes, depending on technical and budget limitation in the design process. Modern expectations are that both eyes view the same image, in other words, a binocular field of view. The second thing, which also comes in the design factor, is collimination. The projected image is colliminated which means the light rays parallel because the light rays are parallel the lens of the human eye focuses on infinity to get a clear image. Collimated image on the heads-up display combiner are perceived as existing at or near optical infinity. This means the pilot eyes do not need to refocus to view the outside world, and the heads-up displays the image appears to be out there, overlaying the outside world. This feature is critical for effective heads-up display. Not having to refocus between HUD displays symbolic information and the outside world onto which that information is overlaid is one of the main advantages of collimated heads-up display. It gives heads-up displays special consideration in safety critical and time critical maneuvers. When the few seconds pilot need in order to refocus inside the cockpit and back outside are very critical. For example, in the final stages of landing, collimination is therefore a primary distinguishing feature of high performance heads up display. The third factor of the design is eye-box. The optical collimator produces a cylinder of parallel light so the display can only be viewed with the viewer's eyes. A three-dimensional area called the head motion box or eye box. Modern heads-up display eye box are usually about 5 literal by 3 vertical by 6 longitudinal inches. This allows the viewer to some freedom of head movement, but movement too far up, down, left, right will cause the display to vanish off the edges of the collimator, and movement too far back will cause it to crop off around the edge. The pilot is able to view the entire display as long as one eye is inside the eye box. The fourth factor in the design is luminance and contrast. Displays have adjustments in luminance and contrast to account for ambient lighting, which can vary widely. Despite of so much benefits of the heads-up display, there were also some problems related to it. Although heads-up display create images at optical infinity, so pilots do not need to refocus between heads-up display and outside view. However, in practice, pilots often misadjust heads-up display focus. This leads to headaches, eye strain, blurred images, and slower response time. Misaccommodation increases error probability during precision tasks such as target tracking or landing. If heads-up display have a narrow field of view, it will restrict how much external world is overlaid with symbology. The key risks were important cues may fall outside the heads-up display area. Pilots may unintentionally rely too heavily on the heads-up display even when its field of view hides critical cues. Tall pilots often lean to stay within the eye box, causing posture-related fatigue or misalignment. The heads-up display and the outside world share the same visual space. While this should improve processing, studies found the opposite. Pilots fail to perceive critical external events. Symbology draws too much attention, causing cognitive capture. External hazards or subtle motion cues become less noticeable. This divided attention is not a skill based problem, it's the limitation of human attention itself. Perhaps the most dangerous problem where heads up display are not attitude indicator. Heads up display symbology alone cannot provide reliable attitude orientation during clouds, fogs, or night. Pilots relying on heads up display cue alone may misinterpret pitch, leading to controlled flight into terrain.